Hi everyone, my name is Siamak and welcome to the ACIGS July 2020 webinar. We're going to have a very interesting webinar today with Professor Malak Bouazza. I'll just go through a few quick introduction slides. As you know, IGS is a global society with more than 45 chapters around the world, and we are here in Australia. Basically, ACIGS stands for Australasian Chapter of International Geosynthetic Society. If you want to access the IGS website, the address is up there, www.geosyntheticsociety.org. And to be able to access the resources, the technical resources, you need to become a member of IGS, and you can do that through the Australasian chapter. And to become a member of ACIGS, you just need to visit our website. Under membership tab, you will see all the information you need to become a member. And that is here, the ACIGS website, www.acigs.org. So we have been doing a lot of events, lectures, and now webinars. We started the webinar series since August last year. So this is almost a year that we have been holding these webinar series. We record every webinar, and as you can see under the resources tab on our website, you can access the recording of all of our previous webinars that you see some examples on the screen at the moment. This webinar today will be also recorded and shared with everyone on the website. So we made this announcement last time. I'll just quickly go through that again because we're sort of getting closer to the deadlines. We have started receiving photos for the competition, as you can see on the screen. This photo competition, you just need to basically go through your photos from sites that you have seen geosynthetics being used or installed on different applications, and email us the photos, and everyone has a chance to send 3 photos. And we will have a winner receiving $500 gift card and the runner-up receiving $200 gift card. And it will be 2 categories, one for general category and the other one is for young engineers or young members who are under 36 years of age. The other important thing is we have been receiving inquiries about receiving a certificate of attendance after each of our events. So this is now possible for everyone who is attending our webinars to receive one of these certificate of attendance. So you just need to email us after the webinar and let us know that you want to receive one of these certificates, and we can arrange it for you to be emailed to you. And today's webinar. So the sponsor for this webinar is Teneo. We thank Teneo for the support of ACIGS and this specific webinar. The topic for today's webinar is PFAS and geosynthetic liners, current status and the way forward. And it will be presented by Professor Malak Bouazza. A brief introduction about Professor Bouazza. So I'm pretty sure most of you guys know Malak pretty well. Dr. Bouazza is a professor of civil engineering at Monash University in Melbourne. He is a visiting distinguished professor at Zhejiang University, China. He has also held a number of visiting scholar positions at Cardiff University, UK, University of Missouri, Columbia, USA, Arizona State University, USA, and also University of Malaysia, Pahang, and Queen's University, Canada. His skills and expertise in the area of geosynthetics and environmental geotechnics are well recognized in Australia and abroad. In addition to his academic commitments, Dr. Bouazza gives specialist advice for the industry both nationally and internationally. His work has included peer review of design for more than 30 municipal solid waste, hazardous landfills, and tailings storage facilities in Australia, Thailand, Peru, and other countries. Thank you, Malik, for your time today and presenting the very interesting presentation. I'm pretty sure we have had a lot of interest in this topic, and I stop from my end and I get you to start sharing from your end, please.
All right. Thanks, CMAC, for your kind introduction. Thanks also for ACIGS for the invitation to present this webinar as part of a long series of webinars that ACIGS has promoted over the past 12 months. And thanks also for Tineo for sponsoring this webinar. Sponsorship is very important, and we are very grateful for Tineo to do so today. Ladies and gentlemen, good afternoon, wherever you might be. It's a pleasure to share today some of my thoughts on PFAS and geosynthetic liners. Over the past 2 decades, geosynthetics have become the solution of choice for waste containment systems. And certainly their use has transformed the way we approach the design of these types of infrastructure. However, this has also brought new challenges as these geosynthetics are increasingly used in more challenging environments, very often exposing them to conditions they have not been exposed to before. The interaction with PFAS substances is a very good example of this situation. So I'd like to share with you today how we can go about addressing the PFAS challenge. And we'll start by one question. Why should we be concerned by exposure to PFAS substances? Well, these chemicals can spread widely. They are pervasive. They are also persistent. They don't degrade that easily in the environment. They can bioaccumulate, and they have an adverse health effect, as has been proved several times. On top of that, we don't know much about them. We have some sort of an incomplete regulatory structure as far as liner systems are concerned, and there's certainly a scarcity of information in literature on the topic. The authorities in various parts of the world were warned about the issue of PFAS exposure long time back, but they were slow to react to it. The reaction accelerated once the PFAS issue started to make headlines of major news outlets, whether they are here in Australia or elsewhere, which of course in turn increased the awareness of the general public. And when you have on top of that books and movies made on the issue, then that awareness increases further, and the authorities are bound to react much faster. Now, what are PFASs? PFASs are factory-made chemicals used in industry and consumer products worldwide since the 50s. Currently, we have about 5,000 compounds which have been identified. Certainly more will be identified in the future as our analytical tools are improving, are becoming more sophisticated. Just think about that. A few years back, we identified only 3,000 compounds. So it was a very big jump within a few years. So these chemicals are useful in reducing surface tension. Therefore, it is not surprising to see that they have been used extensively in non-stick cookware, for example, strain-resistant carpets and textiles, water-repellent clothing, cosmetics, firefighting foams, and so forth. Now here, it's not CIMAC asking me to have a lunch break. These chemicals are commonly added as a barrier to food packaging because they resist water, oil, and grease, and it makes food more portable. A recent study, which has been reported in 2017 by Scheider and al., gave pretty good overview on the spread of their use in food packaging. If you look, for example, at dessert and bread wrappers, they represent about 60%. So 60% of these materials actually are in these wrappers, whether dessert or bread wrappers. If you look at sandwich and burger wrappers, close to 40%. Paperboard for your French fries, about 20%. Why is this important? Because recently a link has been made to health. This has been reported a few weeks back in June, early June this year. The study has shown that women exposed to chemicals commonly used in takeaway containers, like what you have seen before, and non-stick pans, might go through menopause 2 years earlier. And this is just the tip of the iceberg. And certainly more studies will be made available in the near future. Now, all these issues with PFAS, of course, as I said earlier, increase the awareness of the general public, which has led to class actions. This map gives you an indication, this map of Australia giving an indication of where PFAS has been identified. Even a sniff of PFAS is reported here. And you can certainly get an update by going into this website, which reports basically any location within the country where PFAS has been identified. So currently I'm aware of at least 10 class actions in relation to PFAS. Few of them have been settled very recently. The federal government has given the go-ahead for settlement in June this year. They award about close to more than $90 million for the Catherine class action in the Northern Territories here, and more than $30 million for the Oki class action near Toowoomba in Queensland. So, and more is coming. So I look at PFAS. They are very, I would say, complex chemicals. The most frequently PFAS is detected in leachate or surface water close to fire training facilities and the likes are what we call the perfluoroalkyl acids, the PFAS. In particular, so you can divide them into these carboxylic acids and the sulfonic acids, PFCAs and PFSAs. You can also categorize them further by distinguishing the long chain ones versus the short chain ones. So for the long chain ones, for example, PFCAs with 7 and more carbons, such as PFOA, the perfluorooctanoic acid, for example, this is your carbons here, and PFCAs with 6 and more carbons, such as PFOS, the perfluorooctane sulfonic acid. Now, PFCAs and PFSAs with less than 7 and 6 carbons, respectively, are considered as a short carbon chain. So keep this in mind because this is very important, as you will see later on in the lecture. Now, PFAS have a very peculiar molecular structure. They have very long chain tail, which is fluorocarbon chain, CF chain, and then they have a functional head. And this functional head can be either anionic or cationic or zwitterionic or non-ionic. It depends. But that's the one that will react. So this long chain has specific properties. So it is a fluorocarbon tail because it's of the CF connections. It has very strong bonds. Actually, the CF is one of the most chemically stronger bond we know of. It is very stable. That's why it makes it very persistent in the environment. It is hydrophobic, so it is water repellent, as well as oleophobic. No, they have a dual type of properties. It is heat resistant, and therefore it makes sense to see this product used in food packaging. And they can have a very long carbon fluorine chain. Now, don't confuse fluorine with fluoride. They are two different things. So these CF chains can be they can go up to 12, 13, 14, and these were the old ones. So if you look at PFAS in landfills, so PFAS substances have been detected in landfill leachates in various parts of the world. That's because of the disposal of PFAS impacted industrial waste, waste from site mitigation, PFAS bearing consumer and household wastes, which have basically reached the end of their functional life, landfill fires. We had a number of landfill fires here actually in Melbourne, and there were a few others in other parts of the world. What did they use? They used firefighting foam. You also have any industrial, commercial, or consumer products landfilled since the 60s and 70s. So their presence currently is pretty well documented. There's a lot of literature available nowadays giving the breakdown of these PFAS compounds or substances in landfill leachate. Much of this information, at least in Australia, is now incorporated into geochemical indices for monitoring purposes as well as planning purposes. Now, what about the guidelines for liner systems? These are important because the design of lining systems is very highly regulated. At this point in time, unfortunately, information on and guidelines on lining systems accounting for the presence of PFAS substances are non-existent, at least as far as I know. Now, when we are dealing with these fire training facilities, airports, and so forth, very often we need to store these PFAS impacted materials and PFAS impacted soils in what we call on-site repositories or on-site storage facilities. They are often required during either the investigation, remediation, or the construction phases of a given project, or sometimes when other treatment or remediation options are not yet available. Now, these on-site storages can be temporary or long-term, so it depends on, at the end of the day, on the nature of the problem. So you can have storage and content facilities operating for up to 6 months, or they can be much longer in terms of time, and therefore they can be of long-term purpose, more than 5 years, for example. But nevertheless, whether it's a short storage or long storage, they need to be protective of the environment. And we do have some sort of guidance in the country through the National Environment Management Plan for PFAS. And what does this guideline say about these on-site containment? So there is minimum design requirement provided in the document, which includes the capping part of the site. It's a composite cap liner, very often that is proposed, a side liner, composite liner again, and both their aims are to reduce infiltration, obviously to minimize leachate formation, and a base liner, which needs to be of a composite nature to maximize the collection of leachate, therefore minimize seepage issues, and it allows at the same time to monitor and measure the amount of PFAS in the leachate. Now, we also have further guidance on lining systems. So this table comes from a document, and it distinguishes the liner type, whether they are unlined or you have a single composite liner or a double composite liner. At the same time, it gives you an acceptance criteria in relation to these. In this particular case, it's very specific. It's specific to the long chain type of PFAS, PFOS, for example, PFOA and PFHXS. So PFOS is classified as a persistent organic pollutant. PFHX is considered by the health authority as being similar to PFOS, and therefore these two chemicals have been added together. PFOA is actually not has not been identified as a persistent organic pollutant. Therefore, it doesn't figure. It's not classified as such, but it is classified as a class 2B carcinogen. And that means that it is possibly carcinogenic. And this is based on very limited evidence. So these acceptance criteria, again, are function of the type of liners you will select, and these numbers will change accordingly. Now, just for a sense of scale, these figures are reported in nanograms per liter. So 1 nanogram per liter represents 1 drop of water in 20 Olympic swimming pools. So that's quite a small amount, but nevertheless, it is still something that it is not acceptable as far as the guidelines are concerned. So you have these numbers which are quite specific, as I said, to the type of liners you'll be considering. Now, other countries have not gone to the same extent of identifying the lining systems, but they do have figures regarding the screening level in drinking water. And this is a snapshot of these figures. Not many countries, by the way, have these figures. From top of my head, probably no more than 10 around the world. But what this tells you, you can see that there's a wide variation in the guideline levels. And this reflects, in my opinion, the differences in the perception of risks from different countries. And also, probably the uncertainty in the scientific approach taken to assess the risks. So what is very risky in the US is not that probably risky in Canada. So it all, at the end of the day, it comes to the perception. Now, we have pretty well documented information in relation to PFOS and PFOA. What we don't have much is about the short-chained ones. And this table comes from a paper put together not long ago, which documented all these concentration ranges from different countries. And the short-chained ones were very difficult to put together. And in a way, it made sense because most of the focus when it came to PFAS was on the long long-chain PFAS being in large concentrations in these military sites and airports and so forth. The short-chain ones were not that extensive. But nevertheless, there are some guidelines available. You have an indication on this slide here. And again, it's similar to what we have seen before. The figures tend to vary from country to country, depending on that perception of risk. Now, as I said earlier, there's good wealth of information on the PFAS concentration spread in landfill leachate. Over the past few years, I think there were probably now dozens of papers which came out giving an indication and background of different leachates from different type of landfills. So this table, there's an extensive table in the paper. This is just a reduced, less congested table showing you the different ranges that we have picked up from different literature. So this table is actually divided in two. What you have here, these are the short-chained PFAS, and here these are the long-chained PFAS. So the first thing you can probably pick up very quickly from this table is that the short-chain PFAS tend to dominate over long-chain PFAS in most of these landfill leachate. The exception is China, and this is most likely due to the very high loading of long-chain PFAS initially in the waste. This is probably as a result of their extensive use in manufacturing processes. But in general, the trend we see here stems from three facts. The first one, the PFAS manufacturers started to phase out the production of these long carbon chain PFASs. Once, of course, they were added to the list of regulatory substances. So they were identified as a potential problem. And then, of course, they replaced them with short chain PFAS. However, in my opinion, this shift led to the use of much larger quantities of short carbon chain PFAS to obtain the same or similar performance to long chain PFAS. The second fact is that the short carbon chain PFAS are more hydrophilic, and therefore they are more water soluble at the same time than long carbon chain. Therefore, they tend to be more mobile and can be released easily from the waste. And the third and final one, the presence of the short carbon chain PFASs can be also the result of the degradation of the long carbon chain PFAS and other precursors. Of course, all these numbers you see here are function of the landfill age, the waste age, landfill operational processes, climatic effect, location of the site, and so forth. There are many factors that can impact on these values, and this was not taken into account when we put these figures together. Now, if we move to airport facilities, fire training facilities, and the likes, which have been summarized in this table, and again, we distinguish between short chain and long chain. What can we observe? The first thing we can probably pick up is that the short chain concentrations are in general much lower than the long chain. And it has to be expected because the products we have used in fire training facilities and the likes, the foams, contained mostly long chain PFAS, in particular PFOS, which now was probably the largest, represent the largest fraction of PFAS. And it's not surprising when you look at the concentration of PFOS in these aqueous solutions. They tend to be on a very high range compared to the other ones, to the other long chain ones. And because I think they represent about 70% of the PFAS used. Now, if we collapse some of these figures together now, we have seen in the two previous tables, in a diagram such as this one. So what you have here, these are the concentration in nanograms per liter. It becomes apparent that when it comes to the design of lining systems, you cannot have a one-size-fits-all approach. And the reason for that is simply because the dominance of PFAS compounds and concentrations can be quite different if you look at what you have in the fire chilling facilities versus of what you have in landfills. So the takeaway message here is very simple. It is essential to differentiate between the design of liner systems, as they will be subjected to different exposure conditions. Now, what are the implications of what we have discussed so far on geosynthetic liners? Now, typical configurations that we are all familiar with are shown here. You will have your single composite liner, and you have your double composite liner here. And your usual culprit, your geomembrane, your geosynthetic clay liner, as well as drainage systems and so forth. So when we look at these liners, typically used in containment facilities, HDPE membranes, geomembranes, represent a very large portion of what is used. They have been traditionally used in all these lining systems simply because of their excellent chemical resistance and durability. However, in the context of PFAS containment, as I said earlier, a clear distinction needs to be drawn between liner designs for on-site containment or repositories versus landfills, because the challenge facing them will depend on the PFAS compound chemistry as well as the level of dominance in the leachate and their concentrations. What you also know that migration of contaminants through a geomembrane free of defects is usually limited to contaminants that can partition and diffuse into the polymer comprising the geomembrane. And this means that it is restricted to contaminants of organic nature. So in this aspect, the potential migration of PFAS to the geomembrane will be a function of the structure of the polymer, which will be, of course, function of the density, thickness of the geomembrane, its degree of crystallization, the degree of cross-linking, its polarity, as well as the concentration of contaminants and their molecular characteristics. And all this, of course, if you look at the structure of the geomembrane, it's usually product dependent. Now, if you look at our HDPE, it has a structure, molecular structure, as well as a structure of the polymer. Polyethylene is known to be of a semi-crystalline type of polymer, and it has both crystalline and amorphous regions. So what you see here are polymeric chains which are folded in crystal lattice, and this folded chain will form what we call a lamella. You have these time molecules that links each crystallite. This in a way represents the amorphous zones, which are in a way really permeable. We know that the crystalline zones you have here act as impermeable barriers to the diffusion of contaminants, whereas the amorphous zones are more readily permeable, since the polymeric chain or chains are relatively mobile and they are not as densely packed either. So the diffusion process in these amorphous areas is relatively high due to their free volume in sense. It will decrease with the increase in degree of crystallization and cross-linking. That's why, for example, we see more diffusion taking place in LLDPE because it has lower degree of crystallization compared to HDPE, for example. Now, another property specific to polyethylene is its non-polarity. Since it has no functional group at all capable of hydrogen bonding. It's a long chain of carbon and hydrogen which are linked to each other, and they are quite linear. And polyethylene is known to be less resistant to non-polar organic substances such as aliphatic and aromatic hydrocarbons, for example, which can really diffuse through it. And there's a good body of work on that available already. In contrast, polar molecules will tend to exhibit lower affinity with polyethylene and will certainly have a lower diffusion rate through it. Now, what I'd like to do is to go back to the structure of PFAS because it's important. Now, we know that the structure has, in a way, two components. We know that it has the reactive head and it has this long tail, which has a specific characteristic. So the tail group is inert. It does not interact actively with polar or non-polar chemical moieties. However, the head group is reactive and it interacts strongly with polar groups, specifically water. Water is a polar solvent. So assuming that because PFAS are partly polar, then migration through HDPE geomembranes will be limited, can, at least at this point in time, can be misleading because we don't have much data available so far. We don't have published experimental results on this or modeling studies. Unless they become available, then we'll be able to demonstrate the validity of such assumption. So at this point in time, there is no much available, but there's certainly a lot of work taking place in various parts of the world to try to address this lack of information, and this work being done in Canada, work being done here in Australia, as well as other parties, other parts of the world. Now, when we look at this mass transport of PFAS in HDPE, I think it's very important to be mindful of the chemical differences in PFAS between on-site repositories and landfills. We need also to be aware of the challenges that the geomembrane will experience. These challenges will be a function of the level of PFAS concentrations in the leachate, as well as the compound dominancy in the leachate. And this is what we have seen so far. And I think we can probably understand the importance of making these distinctions when it comes to addressing the performance of a given material. Now, with this high concentration, I would like to spend a few minutes discussing one important aspect related to the presence of high concentrations. And this is the formation of what we call critical micelle concentration, formation of micelles. Now, a critical micelle concentration, CMC, is defined as the maximum concentration at which surfactants, PFAS for example, remain freely dissolved in water. Now, as the surface tension decreases because you have more surfactant going into the solution, then once you reach this critical micelle concentration, the surface tension remains constant because that air-water interface is now saturated. And above the CMC value, you have now a number of these monomers staying constant, while these micelles are forming, and they will continue to increase in numbers because you have more surfactant going into the solution. And this is important because the formation of the micelles will be a function of the solution. So in a water, for example, if you look at water as being our solvent in this case, we have the hydrophobic tail of PFAS, and that's this side here, will tend to aggregate together to form the core of the micelles. This is the core. In contrast, the hydrophilic head, because there's water on the outside, so it likes water, it's not water repellent, will be at this interface here, water-air interface. We in contact with, of course, the water molecules, and will form some sort of a corona. Now, if we have a change in solution, so these micelles cannot only form in water, but they can also form in non-polar organic solvents. So in this case, what happens? The micelles aggregates are inversed. So we refer to them as inversed micelles, because now the situation is inverted as respect to water. In fact, what we have is that these hydrocarbons tails now are exposed to the solvent, right? While the polar heads are forming now the core. So they are pointing towards the interior of the aggregate to escape the contact with the solvent. So these reverse micelles are able to hold a relatively large amount of water inside, in their interior. In this way, a pocket is formed, which and becomes very suitable for the dissolution and transportation of polar solutes through a non-polar solvent. And this can be a little bit detrimental to our geomembrane. Why? Because this change in micelle aggregation might facilitate the migration of PFAS solutions through these amorphous zones that we have identified as possibly the weakest link in our polyethylene. And of course, this will be function of the degree of crystallization, cross-linking, and so forth. Now, we also learn a little bit from associated disciplines based on current evidence from literature. For example, for long chain ones, they have been shown to have some sort of irreversible adsorption to HDPE surfaces. And this is when they are on a very highly concentrated, so very high concentration of long chain ones. Whereas for the short chain, they tend to remain in the solution due to their high solubility, but their adsorption to HDPE is almost non-existent. And more recently, the US Transportation Research Board advised all airports operators in the US to use XLPE, the high density cross-linked polyethylene, to store their fighting foam, the HFF. And this was done due to superior stress cracking resistance and chemical performance. The reason is because they have identified failures in the past related to tanks made of LLDPE, as well as HDPE, but which was identified as not really a true HDPE. So they moved straight one step further by making it very specific that if polyethylene is to be used, it has to be XLPE, or you can have a choice of other type of tanks, which can be compatible with PFAS. So what we have discussed so far, especially in relation to, I guess, high concentrations, it seems that the use of more polar-based geomembranes in on-site repository might need to be considered, as they might offer a more robust option to mitigate the migration of PFAS. Now, the other barrier system we rely on, these are geosynthetic clear liners. And again, it's well-known material. It's a sandwich material. I mean, it's composite material composed of bentonite, sandwiched between two geotextiles through a needle punching process to hold the whole thing together. Now, the marionite content or component, which is a significant constituent of bentonite, has a large specific surface area and is capable of both crystalline and osmotic swelling, and it is responsible, obviously, for the desired physical as well as chemical attributes that GCLs are known for. That's why their use is obviously omnipresent in GCL. Just to give you an indication of the importance of the presence of bentonite in the GCL and why it can swell. It's obviously it's hydrophilic. As soon as it gets into contact with water, you go through this first phase of swelling, crystalline swelling. Then when it hits the osmotic, you start to see the interlayers opening, and then you start to see a swelling taking place. And once it is hydrated, it offers you a pretty good material to deal with some of the chemicals we have in our leachate. Now, when you look at the hydric conductivity behavior of this material, there are key issues we usually ask now, we need to deal with. And these issues are in form of questions. The first one we ask ourselves is, can actually the GCL performance be maintained of the life of the facility, the design life? Will changes in contaminant concentrations affect its hydric performance, either in the short term or the long term? Can the GCL meet the performance requirement set up by, for example, the local EPA or regulatory body or other institutions? So what do we know so far? What we know is that we have a pretty wide body of knowledge on GCL compatibility with many contaminants. So there's wealth of information on chemical compatibility. And as a matter of fact, GCL have been investigated very thoroughly for the past 10 to 15 years, past 2 decades. So we have accumulated a lot of knowledge on the performance of GCLs in various applications. What we know is that the bentonite component, when it comes to organic pollutant, it has low sorption capacity, which might be detrimental to its long-term behavior. What we don't know, obviously, is the compatibility with PFAS substances in aqueous solutions. Now, imagine a moment that if we take our GCL as commercially available, and we know that sorption is an issue when it comes to organic pollutant, and we modify the material by adding to it a sorptive material, which might have a very extensive surface area, higher than bentonite, for example. and can have pretty good affinity to organic contaminant. As a matter of fact, if we have identified such material, then we can come up with a product which should be able to minimize the migration of PFAS. And this material can be identified. Activated carbon is a good candidate for this amendment of the bentonite. Why? Because it has very large surface area. It's in the order of 800 to 1500 square meters per gram, much higher than bentonite, which ranges in the 400, 500 roughly. Furthermore, its surface is non-polar, therefore it has an affinity to organic contaminant. So this has been developed in the country actually, and has been challenged by performing hydroconductivity test with landfill leachate as permeant. And this landfill leachate contain PFAS. So this table here shows the concentration range that we have in this landfill leachate. Not surprisingly, you have high concentrations of low chain and short chain PFAS when you compare them to the long chain PFAS. So again, they are more soluble. Their solubility is much higher than the long chain ones. So all these compounds exist as anions, and of course they, as I said, the short chain tend to dominate. So a snapshot of the results. Not all results are presented, but so what you have here, this is your hydroconductivity versus time. This is the reference base of GCL with no amendments, permeate with DI water. So the values are in the range of 310 minus 11. This is what you'll expect. This was done at 35 kPa effective stress. Then if you modify the bentonite by adding activated carbon, you need to see whether it is going to affect the hydroconductivity or not. And what you see here is these activated carbon amended GCL permeate with DI water over a number of days. And it seems that, or it appears that the addition of the activated carbon did not compromise the hydroconductivity that much. Now, if we now look at the amended the activated carbon amended GCL, as well as the non-amended GCL with PFAS leachate as a permeant, we have a different outcome. So what you see here is the amended GCL with PFAS leachate as permeant. You have a hydration phase. This is first exposure type of condition, and then it started to change with time. These tests have been going on for more than a year. It's a year and a half at least, but we are presenting here only a very short snapshot of the results. If you look at the GCL non-modified, it sits here. So one can easily conclude, oh yeah, that's all good. Why did you bother adding activated carbon since the permeability or hydroconductivity is much higher compared to a conventional GCL? Well, if you look at the next slide, that will explain why we need an activated carbon. So what you see in this slide is the range of concentrations for these different compounds. These are the concentration in the leachate therefore the original concentrations. What you see here are the influent concentrations through the GCL after 50 days of permeation, non-amended GCL. So the concentrations are pretty high. I mean, there was, in general, the PFAS concentrations did not reduce much in GCL, the non-amended GCL. The small changes we have observed can be attributed to the presence of hydrophilic functional groups in the PFAS compound, which of course offered some capacity for absorption into the bentonite component. In contrast, the PFAS concentration in the activated carbon amended GCL reduced. It reduces to the level of recording. These tests were done at commercial labs, therefore the level of accuracy is not very accurate in that sense. There is a level of accuracy with the equipment. So up to this level, so all data is fine. But it does show you that the activated carbon has reduced the amount of PFAS going through the GCL. And it's not surprising because there's a lot of work on activated carbon which shows that it is very effective in absorbing PFAS, especially the long chain one, through these hydrophobic interactions. And it seems to be the case in the current investigation. Same talk, it was also reported that short chain PFAS are likely to form aggregates due to their hydrophilicity, and then that potentially might reduce the absorption potential, and that's probably what we are seeing here. But this is very early stage, so these are at 50 days of permeation. There's more data available confirming these observations. So this brings me to my concluding remarks. One aspect that is very important when we look at PFAS through liners is their mobility. Therefore, the evaluation of the effectiveness of these liner systems currently for containment of PFAS is very scarce. And I think this situation is mostly due to the newness of the problem, of the issue, and at the same time, the lack of information on PFAS mobility through these liner systems. We need to be aware of the differences. As I said earlier, it is important to differentiate between on-site versus landfill applications. Therefore, we should not lose sight of the importance of distinguishing liner solutions when we are designing for on-site repositories versus landfills, because the challenges and performance requirements are different. Therefore, limitations and suitability of different types of geomembranes and GCLs for this type of applications need to be acknowledged. Now, in terms of where we need to go, I think from our point of view, it's very important to gain a better understanding of the PFAS complex chemistry. It is the key for the solution. Once you understand the chemistry of the material, then you are able to deal with the next stage, and that is obviously making sure that the material you select is compatible. And this can be exacerbated a little bit further because it can become more challenging once we account for the presence of other contaminant in the leachate mix. Now, if you are an on-site repository, PFAS is not on its own. It's going to be mixed with hydrocarbons and so forth. So you will have partitioning taking place with water, the air, as well as your N-apple, and it makes the whole thing quite complicated. So there is certainly a need to focus a little bit more on that. And in doing so, this should allow us in the future probably a better appreciation of the fate and migration processes that will take place through either the geomembrane or the GCL all combined together, which currently, at this point in time, is posing a significant hurdle to the design, to at least the development of designs that are supposed to ensure a long-term environmental protection against PFAS migration. So this brings me to the end, and before that I need to acknowledge the support of the Australian Research Council as well as a number of industry partners working on this PFAS issue. I would like to thank Dr. John Shears from Excel Plus for his suggestions this presentation, as well as the paper that is based on Mr. Daniel Gibbs and GeoFabrics for allowing me to present some of the work on the activated carbon amended GCL. And of course, the views expressed in this presentation are those of the presenters alone. That's only my views, not the views of any sponsors. Thanks very much for attending. If you need any, after this webinar, if you have any questions or you need some clarifications or you need a copy of a paper which based this presentation, feel free to email me at this address. Thanks again for attending. Thanks again for your attention. I'm looking forward to the discussion session in a few minutes. It's all yours, CMAC. Thank you.
Thank you, Malak. Very, very interesting presentation. I have received quite a few questions actually. So without wasting any time, I'll try to get to a few important ones, and then I think the rest of them I can email them to you, Malak, and if you can kindly answer those, and we can email back the responses to the people who've asked the question. So,
absolutely, yeah.
Perfect. First question, based on slide 31, does it mean that PFAS would diffuse in either a polar or non-polar material?
It will diffuse, but if there's diffusion in a polar, it will be reduced. It will not be the same diffusion rate. So if you look at the membrane, you have, if the polarity changes and the atomic radius of the backbone of the polymer increases, then you are reducing the diffusion process. It's not going to stop it, but it will reduce it.
Right.
So it might be order of magnitude difference, but there'll be certainly a reduction because you don't have these amorphous zones present like you have in polyethylene.
Yep. Then the other question about ACA GCLs that you just discussed it towards the end of the presentation. The question is, do we have info on breakthrough of PFAS in the ACA GCLs?
Yes, we do. But I cannot present them because there is a non-disclosure agreement.
Okay. The other question is, wouldn't positive pore pressure in a compacted clay liner or a hydrated GCL be the primary barrier due to the fact that PFAS are overall hydrophobic?
What I don't understand this question pretty clearly. So is the question related to the existence of a positive pore water pressure? Meaning, correct, if the GCL is hydrated?
Yes, in a CCL or a GCL when they are hydrated, when they are saturated or hydrated GCL.
Yeah, if the GCL is hydrated, you will minimize, because what happens then, the breakthrough time is obviously changing. For example, what I showed earlier, it's all related to first exposure. There was no water in the GCL. So the bentonite hydrated with actually the PFAS substances. In a GCL, if the hydration process takes place with water, then you allow that swelling to, as shown in that short video, to take place. So you are able to allow bentonite to swell to a stage where then it can deal with contaminants. So when you have these solutions coming through, the breakthrough time is obviously now different, because for anything to happen, it needs to dislodge water from the occupying sites, for the binding sites. On the other hand, if we have a lot of mobile PFASs in the system, like short-chained ones, that might migrate, maybe their breakthrough time will be earlier than the long-chained ones.
Yep. And last question, Malak, and I will have another couple of questions which we send them through the email. So the question is, have you modeled the advective and diffusive transport of PFAS through liners?
Well, it's not different from what we have done with organic migration through liner systems. The important aspect is to know the transport parameters. So you need to know, obviously, the diffusion rates through your geomembrane as well as your GCL or any other materials you'll be using. Once you have that, you know the conditions of the site, so you can set your boundary conditions accordingly. But the key is on the parameters. So the parameters need to be identified. This is where the problem is currently. We don't have these parameters. You can err, the only thing you can do is err on the conservative side to model. And that's a feasible solution. You are increasing your safety factor if we look at what we do in geotech engineering. So the parameters are key. The process, and if you look at geomembrane, for example, you need to understand how the PFAS will partition in the geomembrane. So the diffusion test will give you an idea on how it's going to move through a geomembrane. Same through a GCL and so forth.
Perfect. Thank you again, Malak. Very interesting presentation. And as I said, I'll email the rest of the questions to you. And if you can kindly answer to those, we can send them back to the people.
Yeah, no problem. As I said, if anybody who attended or will be watching I guess, the webinar later on, if they have any further questions or clarifications, now they are free to email me directly.
Perfect. Thanks again, and everyone for attending this webinar. As I said at the beginning, the webinar was recorded, so we will upload this to our website for future access. Also, another important announcement is for our next webinar, we have a very interesting presentation by Professor Jorge Zomberg from the US. So I encourage everyone to attend that one as well. Last thing, if you still want a certificate of attendance, please email info@acigs.org or events@acigs.org, and we can arrange that for you. Thank you, Malak. Thanks, everyone, and we will see you next time.
No worries. Take care. Keep safe.
Thanks.
And well. All the best.
Thank you.